In this video, we are going to solve for the molar volume of oxygen using the Lee-Kesler Equation of State. The Lee-Kesler Equation of State is pressure times volume equals Z times the number of moles times the gas constant times the temperature. And the temperature has to be an absolute value, so either Kelvin or Rankine. The only thing that's new, most people haven't seen, is Z, or the compressibility factor. The equation to find the compressibility factor, or Z, is Z equals Z naught plus W, or the eccentric value, times Z prime, or Z1. Z naught is tabulated in your textbook, as well as the eccentric value and the Z prime. However, the Z naught and the Z prime are a little bit different than the W. W, you find it, you can find that one on the internet. You can find it at the back of your textbook. It's unique to the substance that you're using. So the eccentric value will be different for oxygen, for water. So that's just a tabulated value that you can either search up online or look up on your textbook. Z naught and Z prime are tabulated in a different way. In order to find Z naught and Z prime, you need your reduced temperature or your reduced pressure. Reduced temperature is simply your given temperature divided by your critical temperature. And your reduced pressure is your given pressure divided by your critical pressure. The critical temperature and the critical pressure of a substance is tabulated. And you can look up critical temperature of oxygen and it'll tell you on Google critical pressure, and it'll also tell you on Google or in the back of your textbook. So in order for you to understand how we can get Z naught and Z prime, looking through your tables in the back of your textbook, you do it this way. So let's say they give you bromine at 759.2 degrees or Kelvin and 62.01 bar. So you will need to find a reduced temperature, which is the temperature divided by critical temperature. So your T is given as 759.2, and then your critical temperature for bromine is 584 degrees Kelvin. You go ahead and do that calculation, 759.2 divided by 584. You get that TR is equal to 1.3, and then you do the same thing for PR. PR is P over PC. The given pressure is 62.01, and then when you look the critical pressure up, it should be 103.35. So when you do that calculation, you get your reduced pressure being 0.6. So we have our TR of 1.3. So we look at our Lee-Kesler correlations tables, values for Z naught. So I'm going to locate where TR is equal to 1.3, which would be one right there. And then my PR is 0.6, so I'm going to match it up here. And then we look what the value is. For these numbers, it is 0.9083. So hold up, let me make sure. Yes. So my Z naught would be 0.9083. And then we do the same exact thing for the Z prime value. So the same TR, 1.3, same PR, 0.6. We look for 0.6 on the PR. We look for 1.3 on TR. And then we look for the value that it hits. So my value would be right here, and it's 0.0429. 0.0429. My W, or eccentric value for bromine in my textbook, it says that it's 0.132. So in order to solve for Z, we use the Z formula, which is Z equals Z naught plus WZ prime. And we just plug and chug. So Z equals Z naught, which is 0.9083 plus your eccentric value 0.132 times Z prime, which is 0.0429. And after plugging those numbers into your calculator, you're supposed to get 0.91396, depending how much your professor wants you to round. And that's how you solve for the compressibility factor. So let's go ahead and let's do an example. So example 1. Oxygen is contained in a cylinder at a pressure of 100 bar and a temperature of 190 Kelvin. Estimate the molar volume in meters cubed per mole and the specific volume in units meters cubed per kilogram using Lee-Kesler's Equation of State. Alright, so I'm going to go ahead and just write down things that I know. I know that the substance is oxygen. I know that my pressure is 100 bar. My temperature is 190 Kelvin. I'm looking for my molar volume in meters cubed per mole. I'm also looking for my specific volume, which is meters cubed per kilogram. Okay, I think that's all we know so far. And the Lee-Kesler Equation of State is PV equals Z nRT. We're looking for molar volume. Molar volume is the same thing as saying like V volume over moles. So in order to solve for that, I'm just going to divide by moles on both sides. So it'll be P times molar volume equals ZRT. We divide by P on both sides. And we get that the molar volume is equal to ZRT over pressure. Good thing is that we have pressure, we have temperature, we can find our R value. However, we don't know Z. We have to find it using the Lee-Kesler correlations that we just learned about. However, let's go ahead and find R first, or R, gas constant. I know that in order to find TR and PC, or TR and PR, I'm going to need my critical temperature values. So again, you can either look those up on the internet or in the back of your textbook by looking up oxygen's critical temperature, oxygen's critical pressure. And it should be 154.6 Kelvin for the critical temperature and 50.46 bar for the critical pressure. So I'm going to go ahead and now look up my gas constant. I'm going to look at the units that I have. I have my temperatures in Kelvin, my pressure is in bar, and it matches these. That's good. However, I have my volume in meters cubed. So hopefully we have an R value that matches those units so that it will make our lives easier and we don't have to do so many unit conversions. So we're not going to use the first one because it has liters. Second one, centimeters cubed in atmospheres. That seems horrible. Feet cubed, centimeters cubed with torr. Also horrible. This one has meters cubed. That's good. However, our pressure is not in pascals in our problem. It's in bar, and I think we can do better than that. So we're not going to use this one. This one, none match. Centimeters cubed, liters. I like this one because volume we have it in meters cubed, we have our pressure in bar, and it's easy to convert from kilogram moles to moles, gram moles. So I'm going to go ahead and use that as my value for R. Great. So I'm going to go ahead and write down my R value, 0.08314, as well as its units, because it'll keep us organized, and it'll also tell me the units at the end. Alrighty. Great. Let's go ahead and let's solve for Z using Lee-Kesler. So we know that the formula for Z is equal to Z naught plus W Z prime. Our W, our centric factor for oxygen, is tabulated. So I know my textbook tells me that it is equal to 0.288. In order to find my Z naught and my Z prime, I need TR and PR. My TR is equal to temperature over critical temperature, and my reduced pressure is pressure over critical pressure. So TR is equal to 190 divided by 154.6. For TR, when you put that in your calculator, you get that it's equal to 1.2289, which is pretty close to 1.23. It honestly just depends how nice your teacher is with rounding. And PR value is, let's see, when you plug it into your calculator, you get that your PR value is 1.98176, but it's pretty close to 1.98. So I'm going to leave it as PR is 1.98 and my TR is 1.23. Alrighty, let's find Z naught. Okay, my TR value is 1.23, my PR value is 1.98. So I'm going to locate my PR up here. PR is 1.98. We don't have 1.98 specifically. However, so we're going to have to get the two closest values. So 1.98 is in between 1.75 and 2. So those are two important values that we need. And TR is 1.23. Unfortunately, we do not have 1.23 on our tables, but then it lands between 1.2 and 1.3. So we're going to need to do double interpolation. So we look at the values, the values that correspond with those TRs and PRs, and we see that these four values, 0.6029, 0.5605, and 0.7243 and 0.6908 are going to be important, and they are going to be necessary in order to use the double interpolation method in order to find out what the Z naught value is, even though we don't have it at 1.23 and 1.98. So let's go ahead and I'll show you how we do that using double interpolation. So what we do, the way I like setting it up like this. Using this table right here. So using that table, I'm going to write down what I saw in my Z naught value, in my Z naught tables. I had TR and PR values. The TR values I chose were 1.2 because 1.23 is in between 1.2 and 1.3. My PR values that I had to choose were 1.75 and 2. So I'm going to put 1.98 because that's my actual PR value. And the number that was next to it was 2. Alright. the value that corresponds with 1.2 and 1.75 on our tables was 0.6029, and the number that corresponded with PR of 2 and TR of 1.2 was 0.5605. The value that corresponded for 1.75 and 1.3 was 0.7243, and the corresponding value for 2 and 1.3 was 0.6908. We're trying to find out this value right here. We're trying to find P. The formula to find P is this one. This is the formula. What I recommend is to not do this by hand, but either code this into your calculator or code it into Excel or something so you don't have to waste so much time doing it. I'm not gonna do it. I'm not gonna plug and chug. It's literally just plugging and chugging. So x2 is this value here, which for us is this value here. Q11 is this value, which is our value right here. So just a bunch of plugging and chugging, which I'm not going to waste my time doing because we need to move on. After you plug in all of your values into this equation, here I'm going to go ahead and write down code this in your calculator. And if you do that and you plug in Q11, Q21, Q12, and Q22, you get that P is equal to 0.602768, which is about 0.603. So my Z naught value at 1.98 and 1.23 is 0.603. Perfect. That's part of our equation. We still need to find Z prime. And the same way we did it for Z naught, it's the same way we're gonna do for Z naught. So I'm gonna go ahead and pull up the table. And we're not looking at Z naught. We're looking at Z prime this time. Again, I'm going to identify my TR and my PR. My TR is 1.23, but we don't have 1.23. We have 1.2 and 1.3. My PR is 1.98, but we don't have 1.98. We have 1.75 and 2. So the values that we are going to be messing with this whole time will be this one, that one, and that one. So 0.1840, 0.1990, 0.1729, and 0.1991. Now let's go ahead and do the double interpolation in order to figure out what Z prime is going to be at our TR and PR values. So we do so the same exact way we did it with Z naught, exactly the same way. So Z naught, or Z prime, I mean, we're looking for Z prime. Let's remind ourselves that our TR was 1.23 and our PR was 1.98. So TR, PR. So the values we chose was 1.2. 1.23 will be in the middle, and 1.3. Our PR values are 1.75. Then our actual PR value, which is 1.98, and then 2 right here. The corresponding values at those points were 0.1840, 0.1729, 0.1990, and 0.1991. Now again, we're trying to figure out what P is. So what the actual Z prime value is using our TR and PR. We do that by using the same formula that you can either plug and chug, do it like manually, or you can just code it into your calculator or look it up online. It's completely up to you and what your teacher allows. When you plug in all of the corresponding values into this equation, you get, and reminder, right, y2 is this value right here, your q21 is this value right here. They match 100% with the table on the left, so just in case you want to double check. But after plugging it in, we get that P is equal to 0.1975612, which is approximately 0.198. So Z prime is 0.198. Perfect. Finally, we have all the necessary information to solve for Z. Z is equal to Z naught plus WZ prime. So Z is equal to our Z naught, which was 0.603, plus the W or omega or eccentric value, whatever you want to call it, times Z prime, which is what we just found, which is 0.198. After plugging that into your calculator, you get that it's equal to 0.66. Our problem was asking for molar volume. Molar volume is equal to ZRT over pressure. So our Z, which we've just found, is 0.66. Our R value that we chose was 0.08314. Our temperature is 190. And our pressure is 100. Plug that into your calculator and you get 0.1043. And in order to know the units for the molar volume, we're going to go ahead and look at our R values. So molar volume is volume over moles, and our volume is in meters cubed. So volume is meters cubed, and our moles are in kilogram moles. So molar volume is meters cubed over kilogram moles. If you want it in gram moles, you can convert it into gram moles. I don't want it in gram moles. I'm just going to go ahead and keep it like that. And to solve for specific volume, again, they wanted the units to be in meters cubed per kilograms. So I'm just going to do a bunch of conversions. So 0.1043 meters cubed per kilogram mole. 1 kilogram mole of oxygen contains 31.999 kilograms of oxygen. So what's the molar mass of oxygen? You can look that up. And kilogram moles cancel, and you get that the specific volume for oxygen under these circumstances will be 0.0033 meters cubed per kilogram. And that would be your answer for the specific volume. Sometimes you won't have to do double interpolation, though the TR value and your PR value would be nice to you, and it's easy to find in the tables. But in this scenario, you weren't given perfect TR PR values, so you had to do double interpolation. Sometimes you're going to have to do linear interpolations. So this was it for example 1. Make sure you take a look at my example 2 and 3, because I am going to explain how you can find pressure or even temperature using Lee-Kesler's correlations of state.